Okay, so in the original plan for the lectures, it's a bit resonant, I think. Is that all right? Maybe it's okay. Okay, good. I shouldn't be quite so enthusiastic. In the original plan, I was going to talk today about neurons and about behavior, and then tomorrow I was going to talk about embryos. I think in order to make things work, I'm going to talk entirely today about neurons, and tomorrow will be behavior and embryos. And sort of the theme will be today really more analysis, whereas and different theoretical frameworks, whereas tomorrow it'll be about ways of searching for scaling behaviors in unusual places. So that's what will tie the two things together tomorrow. But I think this will be a better balance. So today, we'll talk about order 100 neurons, we'll talk about order 1,000 neurons. So I'll remind you from Monday, we said that one of the ways of simplifying our description of a complex system was to use the idea of maximum entropy. And so as a reminder, if the states of the individual variables in your system are sigma I, so the states of the whole system are the set of sigma I, and you say that you want the averages of certain functions of this state to agree between your model and what you see in the experiment, but you also want to maximize the entropy of your probability distribution, then the answer is that the probability distribution over states has this Boltzmann form where, in effect, each function of the state of the system that you think is important becomes a term in the effective energy. And there's a coefficient, which you can think of as a coupling constant or a strength of the interaction. Now, the problem is that to get to here is relatively straightforward. It's the same argument as deriving the Boltzmann distribution by maximizing entropy at fixed average energy, just with more indices. The hard part, as I mentioned, is to figure out how to set these coefficients so that these conditions
like so much of that's in your Berkeley innovation that explains it.
Yes. Does this work now? It's funny, yesterday everything was completely smooth, and today, at first I couldn't connect the computer, now we have problems with the audio. Anyhow. Oh. Hang on just a second. Maybe the problem is that I haven't muted myself. How about that? Yes, very good. That should be better. All right, sorry about that. Yeah. Let's stop. That's okay? Good. All right. Okay, so the problem with this is that this is a formal solution, and it has this collection of coupling constants or coefficients in it, which came from the Lagrange multipliers that enforce this condition when you did the maximization of the entropy. But then you have to figure out their actual value. And in some sense, you can think of that as sort of having to solve this on the right-hand side are things from the experiment. On the left-hand side is something that you would calculate from this distribution. So it's a function of these g's. So you have to solve this equation. But that's a nightmare. In small systems, you can actually do it. But we're not interested in small systems. So by the time you're talking about 100, when this index runs from 1 to 100 or even 1 to 40, you can't do it. So what do you do instead? Well, you're trying to get the average over the probability distribution to match the experiment. So you take this probability distribution, and after all, it's a Boltzmann distribution with some funny energy, and you do Monte Carlo. Right? So you simulate the states of the system by drawing out of this distribution. So by Monte Carlo, you can estimate the average of f in the distribution P. And you can ask, how close did you get? So you pick some set of g's. Of course, you didn't pick the right ones. But go ahead, anyway, compute the average of f mu. You'll find that it's not equal to the average of f mu in the experiment. So what do? Well, you should change the value of g mu, and you should change it in proportion to how far away you are from the right answer. So let's put some coefficient here. And now we have to get the sign right. You'll notice that if I make g bigger, then the average of f mu will get smaller, right? Because it's e to the minus g. So if this thing is bigger than this, I should make g bigger, so I've got the sign right. Okay? So what you do is you set the problem up. You take some initial guesses about the g's. You simulate. You adjust the g's according to this rule, and you keep going until this condition is satisfied to some accuracy that you decide on. And that accuracy, a logical choice is to think about the experimental errors in the measurement of this quantity. Okay? Now, so that's what you do. Now, there are various tricks you can do to speed things up. Some of you may be experts in Monte Carlo simulation, and you know that there's a whole world of things you can do to be more efficient. I'm actually not expert on these things, so I could tell you about them, but I'd just be telling you about things I learned by reading papers, so you could read them too. I do want to point out one thing which is important, and that is that if you imagine that my data is a collection of states of the system measured many times, so n goes from 1 up to, I need a different, let me explicitly say it's the number of samples. Now, if you could arrange that these samples were all independent of each other, then the probability of your data would just be the product on n of 1 over z e to the minus the sum of g mu f mu of sigma I n. And so you might say, I don't know about this maximum entropy business, But if you give me a model for the probability distribution, and it has parameters, I know what I'm supposed to do. I'm supposed to maximize the likelihood of my data. So what I should do is keep changing delta G mu to be proportional to the derivative of log of P of data with respect to G mu, right? So I'm sitting here at some value of G, I compute the gradient in the likelihood of the data, and I go up the gradient. So I will leave it as an exercise for you, and remember that you get expectation values in statistical mechanics by taking derivatives of the partition function, that this is actually that. So if you say that what you've done when you make the maximum entropy construction is you said, there's certain functions of the state of the system that I care about, and I want to get those right. And that tells me that the form of the model is a Boltzmann distribution in which each one of those functions gives you a term in the energy. But then you could say, okay, forget about the connection to physics. What you've done is to define a family of probabilistic models. Within that family, find the one that fits the data best. Same thing, it's the same as enforcing the expectation values. So sometimes you hear people talk about, what's the difference between maximum likelihood and maximum entropy? Well, if you need to say what you mean by those words, but if you say it correctly, the answer is there isn't a difference. Okay. So now, okay, is this clear? Let me emphasize that if your system is large, doing the Monte Carlo simulation can get a little bit expensive. Okay. You know that. So the problem, as we kind of talked about on Monday with various questions, is what functions of the state of the system should you choose? So we're going to talk about neurons. And actually, I'm going to, yes, and then at the right moment, I'll turn it off. In fact, okay, getting everything to work at the same time is too hard. There we go. Now we know it's not the right time to look at the screen. So we're going to talk about neurons. And so for convenience, what I'm going to do is I'm going to talk about, in the first instance, I'm going to talk about the states of neurons, a collection of n neurons, but at a single moment in time. And as Mauro pointed out, the good news about recording action potentials is that you have an intrinsically binary signal coming from the neurons. The bad news is that you have to decide with what time resolution you're going to measure it. And there's a little bit of arbitrariness there. So there are various, by the way, you could imagine trying to take a very different point of view, that instead of taking a small window of time and saying, spin up if there's a spike and spin down if there's no spike, you could say that the spikes are like a gas of particles that live along the time axis. And you're interested in their position along that axis. And you should somehow think of them as a gas of discrete particles rather than the sort of lattice version that you get with the Ising model. So maybe some of you remember the equivalence of Ising models and lattice gases, right? So there's a path there, which, by the way, I think nobody has actually taken, but so there's things to do. So how am I going to choose my time bin? Well, as Mauro pointed out, if you choose your time bin to be very large, you're sort of averaging lots of things together in some way that doesn't make any sense. If you choose your time bin to be very small, then to first approximation, nothing ever happens in the bin, and occasionally one thing happens, which is to say one neuron generates an action potential, And that doesn't give you any access to the collective behavior of the network because you've made your bin so small that only one neuron is active at a time. So you know all the states of the system. The states of the system are 1, 0, 0, 0, 0, 0, 0, 0, 0. And it's always that. Which one is the 1 changes, but nothing interesting ever happens. So what you want to do is to look at the one thing you can do is to look at the correlations between pairs of neurons. And what you'll find if you measure the cross-correlation function between the spike sequences is that in many systems, there is a sort of slow, long-time correlation. But then there's a sharp peak in a small window of time of order 10 or 20 milliseconds. And so if you choose that as your time bin, then the probability that you get that a single neuron produces 2 action potentials in one bin is still very, very small, so the response is binary. But on the other hand, you've integrated over all the strong whatever correlations there are between the neurons. So let's do that. We'll choose a time bin, and then in every time bin, we look at the state of the system, and each neuron is described by a variable sigma, and I think I'm going to consistently use sigma is 0 or 1 for silence or spiking. You all learned statistical mechanics thinking about Ising models in which sigma is plus or minus 1. You realize that you could rewrite it all in terms of 0 and 1. I actually once worked for some years at an institute where there were physicists and computer scientists. And if you ask a physicist about a binary variable, they'll always tell you it's plus or minus 1. And you ask the computer scientist, they'll always tell you it's 0 and 1. And you would be surprised how much confusion this actually generated among a group of rather well-educated people. But okay, why am I going to do this? There's a couple of reasons. One is the reason you do the plus or minus 1 in the case of the Ising model is because you're trying to use a notation which naturally captures the symmetry between spin up and spin down, which is of course broken by a magnetic field, or spontaneously broken if the model magnetizes. But there's no symmetry between spiking and not spiking. Neurons mostly don't spike. So you're not buying yourself anything by using a symmetric representation. In fact, you're costing yourself something, because if you write everything in terms of sigma I is 0 and 1, then every time you write down a sigma I, mostly it's 0, which is convenient, because that means that you can use sparse array techniques and things like that when you have to actually compute something. So what choices am I going to make for the F mu? Well, so this is silence or spike in some window of delta t, which might be something like 20 milliseconds. So what do I pick? Well, we know that if neurons are more active or less active, it matters. So let me pick sigma I itself as one of the F mu's, which means that I'm going to insist that the average of this comes out to the average in the experiment. And what that means is that if you count how many action potentials on average do you get from a particular neuron, the model will get that right. But in order to say something about the behavior of the network as a collective, you have to do more than that, right? Because you have to tell me that the neurons are correlated with each other in some way. So you may remember that on yesterday, I showed you a picture of the growth of the number of neurons that people are recording from simultaneously. If you go back to the origin in the 1960s, well, it's not interesting when it's 1. I mean, it was interesting for a long time when it was 1, but okay. People did 2, and they spent a lot of time thinking about the correlations between pairs of neurons. And this kind of conditioned our thinking in the field And so if you ask people, tell me something about the correlation structure of a network of neurons, they tell you about the correlations between pairs of neurons. Not obvious that that's the right thing to do. There's a kind of specious argument for why it's the right thing to do, which is that if you built a dynamical model of a neural network, then the architecture of the network would be encoded in the pattern of synaptic connections. And the pattern of synaptic connections is a matrix. And so if you think that the pattern of connections is the dominant thing dynamically, the object that's sort of the same size and plausibly related to it is the matrix of pairwise correlations. So another thing we can do then is to insist that we get the pairs right. Okay? If you do this and you plug it into here, I mean, we now have a slight notational shift, right? Because here I had k different functions. Here I have n functions, one for each neuron. And here I have, well, n times n minus 1 over 2, but roughly speaking, n squared functions for every pair of neurons. So capital K is now a number of order n squared. So there's a lot of them, but that's okay if you have enough data. And if you plug this in to here, then you get a model which is, so if you think of this as e to the minus some Hamiltonian, or let me not call it a Hamiltonian because that has dynamical consequences, let me call it an energy function, then the energy function can be written this way, and you recognize that as an Ising model with pairwise interactions. Except I've done something funny, I have a 0, 1 rather than a minus 1 representation, but that doesn't matter. And there's a magnetic field. Why is there a magnetic field? Because spiking and not spiking are not symmetric. Okay. There's also a sign convention. To be consistent with what I did on Monday, I chose the sign convention this way. I find it much easier to think about this one. Right? So now a positive field turns the neuron on, and a positive coupling Jij causes neurons I and J to do the same thing. It's a little more intuitive, I think. But of course, as long as you keep track, it doesn't matter what you do. Okay? So, yes? Actually, the figure that I'm about to show you on the slide, I think contains the answer. So if it doesn't, ask it again in just a minute. So we first tried to do this. You'll remember the first examples of recording from large numbers of neurons were in the retina. So we had the good fortune to collaborate with Michael Berry's group at Princeton, who was one of the people who had been developing these techniques starting from when he was working with Marcus Meister. And so this was our first try. So here you see the action potentials from 40 different neurons as a function of time. Here's what happens if you blow up a small region of it and look on much finer time scale. If you look at the correlations between pairs of neurons, you see a structure that looks like this. So if you want to, what you say, the correlation function that's being plotted is, if I tell you that neuron I spiked at time 0, what is the probability per unit time that neuron J spikes at time, well, tau, which isn't written there, sorry. And so you notice that if you go far away, it stabilizes at what is the average probability of that neuron firing. but if you look inside, you see a peak, and the peak is perhaps 20 milliseconds wide altogether. So that's why we chose 20 milliseconds, to capture those correlations. So if you do that, then it turns out that in each bin of width 20 milliseconds, the probability that a single neuron produces 2 spikes is essentially 0, and so, well below 1 in 1,000. And so you can convert these into a binary representation, which are the sigmas I was just talking about. A very important fact, which is true in the retina, by the way, in these experiments, the retina is being shown a movie of some naturalistic scene. You can also do it in the dark. You can do it with simplified signals. That's a whole axis to explore, which if somebody's interested, they can ask. But you know, like with Maro's 27 different plots, I'm going to try to give you a guide that doesn't explore every alternative. So a very important feature of the neurons in the retina is if you take these binary variables and you correlate them, the correlations between pairs are always weak. So if you look at the correlation coefficient, you see that 10% is way out in the tail. So if I show you 2 neurons, and you make the approximation that they're independent of each other, you're only making a 10% error. However, if you record from 40 neurons, and you ask, what's the probability that k of those n neurons are firing in the same window, if they were independent of each other, you'd get this. But actually, you see this, which is almost an exponential tail. By the way, although I think neither of us have made much out of it, this is the object that Maro was talking about when he went from thinking about avalanches to thinking about spike train data, right? That you should just count how many spikes you see in the window rather than trying to say, I should start counting here and stop counting there. Let me just take fixed windows, count how many spikes I see. So what this means is that although at the pairwise level, correlations are very weak, at the level of the network as a whole, they're enormously significant because if you ask, what's the probability that 10 neurons in a population of 40 generate an action potential at the same time, the answer is that it's small. It's only 1 in 10,000. But that's, well, you can decide how to extrapolate down here. That's somewhere between 2 and 3 orders of magnitude larger than what would be if the neurons were independent of each other. And of course, if you look carefully, you'll notice that something also, right, if you're going to make the tail longer, you have to do something at the other end too, but that's a smaller effect. Okay, so 40 neurons when we started 20 years ago was a lot. So we tried 10. And 10 is big enough that I hope you'll agree some interesting things happen, but small enough that you can actually do this thing without doing Monte Carlo. It's also small enough, right, that since neurons are binary, if I have 10 neurons, there are only 1,024 possible patterns. And the experiment is long enough, it's a few hours, that you can actually sample the distribution of the actual patterns. So we're making a model of the distribution. And normally the argument would be, well, one of the reasons you need a model is because there's exponentially many states, so there's no way you're going to measure all the probabilities. Well, if n is 10, exponentially many is 1,000, and you can measure all the probabilities. As soon as we get to n equals 100, you can't do that anymore, right? But we can take advantage of that because we can ask, and this was a concession to conventions of neuroscience, not to measure the probability of the pattern occurring, but the rate at which those patterns arise in the sequence. It's just a factor of delta t, right? But okay, there's history behind that. You can think of this as the probability that the pattern occurs. And of course, not all patterns occur, so if you look carefully, you won't find 1,000 dots. Some patterns are very rare. Over the course of an hour, they might occur only a few times. If you pretend that the neurons are independent of each other, then you would predict the not terribly visible blue dots as your approximation to the rate at which they should occur. Now you notice there are two things. One is there's a lot of scatter around the straight line, but the scatter is structured. So these are all the states in which there is one neuron. This is the state in which 0 neurons are active. These are all the 10 states in which 1 neuron is active. These are the states in which 2 neurons are active, and so on. And they kind of group together in this way. And you'll notice that the approximation that the cells are independent, not only is it scattered, but the predictions are actually anti-correlated with the data. So obviously, globally, they're correlated with the data, but that's because spikes have a low probability. So states with more spikes are less likely, and that's why there's a general positive slope here. But if you take that out and ask about the patterns, the predictions of an independent model are actually anti-correlated with experiment, which is amazing because correlations are only 10%. So something collective is going on that causes these effects to pile up. So let's build this model and see what you get. And the answer is the red dots, and you'll notice that now you've collapsed onto the line. And in fact, you have, although it's not shown so clearly here, you have actually gotten within experimental error. Okay? So what that says is that the pairwise correlations, although they're very small individually, they're very widespread. You'll notice that there's no resolved peak at 0, right? It's continuous. It's not like there's the pairs of neurons that aren't correlated at all, and then there are the ones that are correlated. And the experiment is long enough that the threshold for statistical significance of the correlation is almost invisible on this graph. Okay, so all pairs are correlated very weakly. So if you think back to your statistical mechanics class, you may remember thinking about the mean field model, the mean field ferromagnet. So in a mean field ferromagnet, maybe you didn't do this part of the calculation, but if you check, you'll find that all pairs of spins are correlated with each other. But the strength of their correlations is 1 over the size of the system. So that means that when you have widespread but weak correlations, that's enough to generate non-trivial collective behavior. And the mean field model is a very concrete example of that. Okay? So this was 10 neurons, although, as you can see, our experimentalist friends were already recording from 40 neurons, so we needed to up our game a little bit. And at the next, we did various things, which I'll skip over, but at the next generation of electrode arrays, which are the ones that I showed you yesterday, where you're recording from 100 or 200 neurons, we decided to jump back in. And you'll notice here that, well, actually, you can't see it from here, but because this is for 40 neurons altogether. But if you did this plot for the 10 neurons, that we're describing here, what you'd find is that the theoretical prediction for this curve is really quite good. And in particular, you predict the probability that the entire population is silent very accurately. And that's a good thing, because that probability, as you can see, even with 40 neurons, that probability is almost a half. So the network is silent most of the time, which means that your estimate of the probability of it being silent is very accurate. If you just do all this over again with 40 neurons, you discover that your prediction for the probability of being silent is off by 1%. So you might say, well, you know, this is biology. But remember what I said yesterday, when the data get better, you need to ask more of your theory. And the error bar on that 1% is incredibly small. So the error bar on that probability is incredibly small. So 1% is actually a big error. So what we decided to do was to say, okay, this is a model in which you should be careful interpreting this as really being statistical mechanics with variables interacting with each other in an energy. But if you let me do that for a moment, this is a model in which the neurons talk to each other in pairs, like through synapses. But remember, we're recording from some area, and the architecture of the retina is such that there are other neurons that are not projecting out, which we're not recording from, and many of those can touch large numbers of these ganglion cells at the same time, and some of them are inhibitory. So you can imagine that in addition to local interactions, there's also a kind of global regulation of the activity of the system. And that's somehow folded into this prediction for the probability of how many neurons are active at once. So to see if we can get that right, let's insist that if we add up the activity, let's see, maybe I should plot it as script P, that sum of sigma I is equal to K, should equal the experimental value, right? So if I think of this as this is the probability, you get the value, the number of neurons that are spiking in the same window is just the sum of the sigma I variables. So if I want to do this right, if I want to capture that, I can just add that as a constraint. And you might say, oh, you're cheating, you're adding lots of constraints. Well, no, you're not. You already had n squared constraints from here. So this is at most n more. So it's not bad at all, okay? You haven't made your model significantly more complicated. And if you think about it, what that does is to add to the energy function a potential, which depends only on the summed activity. So what happens when we do this? Okay, so this is a very quick tour. Very quick tour. First question, we're looking at 100 neurons. That means there's 5,000 parameters that we have to, 5,000 coupling constants that we have to learn from the data. I told you we had a lot of data, but maybe you don't believe me, or maybe we shouldn't believe ourselves that that's enough data in order to do this consistently. So what you can do is to ask, well, at the end of this algorithm that you ran, how big are your errors? And the answer is that so how close did you get to satisfying this equation? And those errors, it turns out, have the same distribution as the experimental errors. And then you could ask, if you compute the probability of your data, or the likelihood, the log probability of your data, and you do it when you build a model for 10 or 20 cells, which is small enough that surely you don't have a problem, you can learn the values of all the coupling constants from 90% of the data, and then compute the likelihood on the remaining 10% of the data, and ask whether it's different, right? And the answer is no, they're not different, and that statement is true at the 1% level. But you shouldn't be surprised that that works when there are 10 neurons, but it still works when there are 100 neurons. So that tells you that you have no problem. I mean, you can actually solve these, and you can solve these equations, and the thing you're putting on the right-hand side is meaningful. Okay, so that's just to be sure that you're not fooling yourself. How well did you do? Well, let's try a few things. This is a model that's built out of pairwise correlations. So I could compute the triplet correlations, right? So the probability that 3 neurons fire together, how much more likely are they to do that than you would have expected from independence or from the pairwise correlations? And you can look at the experimental value and the predicted value. If you don't include this extra term to keep track of the global activity, then you get the black curve, black data, which is pretty good but not great. In particular, you're sort of doing something funny at negative triplet correlations. When you include this effective potential, things are much better. And if you zoom in on the region where most of the data really lie, you do very, very well indeed. You're a little bit worse than the experimental errors, but not much. I will remind you that when you have 100 neurons, there are 100,000 triplet correlations. So when you say you're getting them right, you're getting a lot of things right. Another thing you can do is a fundamental quantity in these models is this effective energy. So I can compute the effective energies from states that I get out of a Monte Carlo simulation, but I can also compute the effective energy for any state that I saw in the data. And I can ask whether those distributions agree with each other. And to emphasize the long tail, this is the cumulative distribution, so the probability that the energy is larger than something. And again, well, your choice of 0, 1 makes it easier to put the 0 of energy in the right place, but okay, never mind. You see the data and the theory, or possibly the theory and the data, I don't remember, but I hope you'll agree that it doesn't make too much difference. As the energy gets larger, the probability that you see any particular state goes down, but of course the density of states goes up, so it doesn't go down as fast as you might think. These are the states that should occur approximately once on average in the course of the experiment, which is measured in hours. This is an energy which is 20 times larger, which means these states are e to the 20th times as rare. And if you work it out, somewhere around here, there are the things that should happen once a year. So you might ask yourself, what are they doing on our plot, since the experiment was only an hour long? And the answer, of course, is that there are lots and lots of those states. So it's not that we measured their probabilities, it's that we saw states that the model assigns this large energy as often as we predict you should. Okay? Because the system is interacting, activity really is collective, right? It's not each neuron deciding on its own whether to be active or spike or be silent. You can take this energy and ask, how does the energy change as I flip one neuron from being silent to being active? And since these things are binary, you can think of that as being like an effective magnetic field that acts on each neuron, which is contributed by the rest of the network. So since we have the actual energy function with all the couplings, we can go through the data and compute what that effective field is for each individual neuron, and then ask, when we find the effective field to be in a certain narrow range, what is the probability that that neuron is active in the data? And that's what you see here. This is the distribution of the effective fields. I think we've now flipped the sign again so that, no, the sign is still right. So negative fields correspond to the neuron being off, which it is most of the time. You can see that the probabilities do a pretty good job of following the expected sort of logistic function, which doesn't have any free parameters, right? Because if you know the effective field, you know the probability of being spin up. This is something you get by averaging over, you accumulate this distribution by accumulating across time and across neurons, but you could sort of unfold this and ask yourself, well, if I'm at this moment in time, the rest of the network is in some state, so I have some probability of being active. And then at the next moment in time, the network has some state, and I have another probability of being active. This is the retina, so you're showing it a movie. What you could do is to compare the probability that you get by looking at the rest of the network with the probability that you get by asking what happens when I repeat the same movie. And so that thing of looking at the probability of a single neuron being active as a function of time in a movie is very standard. They're called post-stimulus time histograms. If you look at 10 neurons in the network, you don't get very interesting predictions. But by the time you're looking at 120 neurons, you're putting the little peaks of probability in all the right places, and you're getting the complete silences right as well. And it's important to emphasize that this prediction involves looking at what the rest of the network is doing, but not at what the visual input is. In fact, building a model that takes the visual input and generates as good a match to this as we see here is actually very hard. There are now deep networks that can do it, but those are very complicated models, and of course, only very recent. You can also ask about the probability that you see the same state twice, but I'm going a little more slowly than I wanted to. Okay. So that was the retina. Let's go back to the hippocampus, right? Where you have these experiments where you genetically engineer the mouse, you have a fluorescent protein whose fluorescence you can monitor that gives you a sort of low pass filtered version of electrical activity. Now, the time bins that we choose are determined not by measuring correlations, but by the fact that it's a movie, and the movie has a frame rate. So you can't go below that, and it's already a little long, to be honest. So that's what we pick, 1/30th of a second. And now I'm going to show you a very complicated figure. Oh, actually, this one's not so bad. So when we first did this, our collaborators were recording from 100 neurons at once. And then by the time we'd figured out how to do 100 neurons, they were on to 1,000. Sometimes, I mean, the usual view is that experiments are slow, but I don't know, sometimes theory is slow too, especially if you're analyzing data. So this is a field of view with 1,000 neurons in it. The old experiments looked at a small field of view that only contained 100 neurons. So you can draw a little circle and that contains 100 neurons. And if you look at those neurons, their correlations, again, are very weak. But, you know, as Mauro was saying, in a lot of experiments, you record from a large area, but only very sparsely. So imagine that you were recording from this whole area, but you could still see only 100 neurons, and you picked them at random. Well, don't quite pick them at random. Pick them so that their distribution of pairwise correlations looks very similar to what's here. And of course, the way to do that is to march through increasingly larger areas, right? Each time, include all the neurons, swap a few of them around so the distribution of correlation stays the same. So if I didn't show you these pictures, this would be a data set with 100 neurons in it, and this would be a data set and 100 neurons in it. And if you only looked at average activity and pairwise correlations, you couldn't tell the data sets apart. But they're different. So let's try all our tests. So here's the probability that k out of the n neurons are active. And if you look very closely, you can see that there are two curves, one from the theory and one from experiment, but they're on top of each other. As you sample more sparsely from larger areas, the agreement gets worse. Here's the distribution of energies. Here's the triplet correlations from theory and from experiment. This is a closer look at the triplet correlations, which is to say, let's find all the places, all the triplets where we predicted that the triplet correlation should be value C. And let me get a little bin so that I have a few triplets, enough triplets in there that I can say something statistical. And let me measure my RMS error in my prediction. But there's also an RMS error in the measurement of the triplet correlations themselves. And you can see that those are on top of each other. So in this case, we're reproducing the triplet correlations as accurately as they are measured. And again, if you sample from a broader area, sparsely from a broader area, you don't do as well. Here's those plots of probability of being active as a function of effective field. Again, you do almost perfectly if you sample densely from a small region, much worse if you sample sparsely from a large region. I'm not going to talk about this one. Let me talk about this one for just a moment. As with the retina, you can take this probability of being active as a function of the state of the rest of the network and unfold it in time. And if you do that, then in a small group of the neurons, you see that the probability of being active goes dot, 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 and they're predicted to be active in sequence. This is not surprising, because this is the hippocampus, and in the hippocampus there are these famous place cells, which are active when the animal is in a particular point in space. And what the animal is doing in these experiments is running along a track. Well, virtually. So the neurons with the place cells that are in order in space should be activated in order in time. But you'll notice something interesting, which is that this time when the animal runs across the track, it is predicted that they'll basically all be active in sequence, whereas in this case, it's predicted that some of them will be missed. So this phenomenon of missed place fields has its own literature, and it's generally viewed as just being noise, because what the cells are telling you about is place, and if you miss firing when you're in the place that you're supposed to report on, that was noise. But it's not. This predicts that it's not noise. It's a collective behavior of the network. The neurons are sharing information about something else, and the something else told these guys to shut up during this period. And by the way, they did. This is the real data of where they were active and where they were not active. So the animal's doing the same thing along these two trajectories, but the network is going through different states, and as a result, these neurons are predicted to behave differently. If you thought that the neurons were only responding to where they are, you'd get this prediction, which of course is wrong. So, what does this have to do with the ideas of criticality that you just heard about? Well, I've written down a model in which the probability distribution of states looks like e to the minus an energy function. Right? So this is a statistical mechanics problem. You could ask, if I imagine that the number of neurons becomes large, where am I in the phase diagram of this class of models? Or alternatively, what's the thermodynamics that goes with this statistical mechanics problem? So a useful thermodynamic signature is to think about the variance of the energy, which, as you all know, is also related to the heat capacity. I find myself continuing to put a V here, not because you should worry about whether the retina is a constant volume, but because the C for heat capacity needs to be distinguished from the C for correlations. So it's useful. Sorry. You know that at a critical point, at many critical points, the heat capacity diverges. So can we see signatures of that diverging heat capacity? What does that actually mean in a finite system? It means that the heat capacity, right, the specific heat diverges, which means that the heat capacity grows faster than linearly in the size of the system. Okay. But I have one retina under one set of conditions. What do? I measure the heat capacity and I get 37. Is that on the way to diverging or not? I can't tell. So I can change the number of neurons that I look at, but I need to change something else to see if I'm at a peak. So one thing I could do is to just say, let's create a fictitious temperature. So what am I doing when I put in a fictitious temperature? I'm simulating a family of possible networks. At one, in the middle of that, at beta equals 1, there's the real network. At beta equals infinity, 0 temperature, there's a network that's just trapped in its highest probability state, which is pretty much silent, so it's basically off. And at beta equals infinity, the neurons are free to flip on and off all they want to, and in fact, since that also swamps the magnetic field, they'll flip on and off with equal probability, which is starting to sound a little weird. So slightly better is to notice that the energy consists of single neuron terms, which are the H's, and interactions, which are, for example, the sum on Jij, sigma I, sigma j, and maybe there's a potential. And what I could do is to reweight these, putting a factor here and adjusting these. And what am I going to do? I'm going to make the interactions stronger or weaker, but I'm going to adjust the magnetic field so the mean activity of the neuron stays the same. So now what I've done is to create a family of networks which the average activity of all the neurons is the same, but at alpha equals 0, they're independent of each other. At alpha equals 1, they are as correlated as you see them to be, and at alpha equals infinity, they're sort of locked up, always having to be slaves to each other. So what happens is that if you look at the specific heat, so this is now the specific heat, right? That is to say, CV divided by capital N, as a function of this alpha, right? This is just to remind you of what's happening to the correlations. At small n, you see some broad peak. As n gets larger, the peak, first of all, grows in amplitude. And remember, you've already normalized by n, so this is telling you that the heat capacity is growing faster than n. And the peak is getting higher, and the location of the peak is moving toward alpha equals 1. So if you think about what you would have seen at n goes to infinity in a genuine second-order phase transition, you'd of course see something that's divergent at this point. And so you can decide whether you think you're on the way to that or not. And there are other things you can check too. The description here is for the distribution of states at a single moment in time. And you'll remember that there's this other view that goes back to the idea of avalanches, that you should always be thinking about how things vary in time. So there's no reason why you can't do the whole construction, not for the single state at one moment in time, but for sequences of states. The problem is that it gets very complicated. So what Thierry Morat and Olivier Marr did was to say, let's look at time dependences, but instead of trying to get all of the states right, let's let the time-dependent things, so my energy function has a sum over times of, let's say, E1, that's a function of sigma I at time t. And then I'm also going to add a potential that depends on how many neurons are active. So again, sort of in the spirit of this term, but now letting those couple to each other at times that are a little bit advanced from each other. And if you do that, you can get very good agreement, again, with triplet correlations, which is interesting and worth talking about. But the thing that I want to draw your attention to is you can ask exactly the same question about the behavior of the specific heat, and this is what you get. In blue, you treat every time bin as being separate, and then as you move toward red, you allow for interactions among more and more distant time points. And you can see that as you include interactions across time points, the peak in specific heat gets dramatically larger and moves to within 1%, note the scale here. This is a plus or minus 10% in temperature. So this peak is within 1% of the actual model. So in an interesting way, that has something to do with what Maro's been talking about for the last 2 days, but I don't think we understand exactly what the relationships are. If you think about the distribution over sequences of states, you see, if you look at the distribution of states at a single moment in time, you see signatures of critical behavior. But if you look at the distribution over sequences of states, you see even clearer indications of critical behavior. So somehow these are wrapped up with each other, okay? So I think that's all I have to say about maximum entropy models. The problem, just so that you know where we are as a field, is that I told you that at 100 neurons, we're not overfitting. If you went through exactly the same exercise for 1,000 neurons, you'd be overfitting. So yes, 1,000 neurons is computationally harder than 100 neurons, and that's a limitation of our algorithm, but that's all nonsense. The real problem is that if you have 1,000 neurons, you don't actually know the matrix of pairwise correlations. You know individual elements of that matrix, but you don't know the whole matrix because you don't have enough data. Let me remind you that if I have n samples, the rank of a correlation matrix can never be larger than n. So if I hold the number of samples fixed and expand the number of neurons that I'm recording from, eventually even the rank of the correlation matrix will be determined by the length of my experiment and not by the dynamics of the network. And long before that, you've significantly distorted the character of the matrix. I mean, there's a whole field of random matrix theory that's about this, but I think it's an interesting thing to think about, that we often feel like I measure something, and I can do it with a small error bar, and then I can measure another thing, I can measure another thing, and measure another thing. The problem is if you're always measuring them from the same data set, the errors in them aren't independent of each other. And so actually, you don't really know all of them as a set, although you can know them individually, which is interesting. So one of the problems that lots of people are thinking about is, are there generalizations of the maximum entropy approach in which instead of constraining all of the pairwise correlations, you constrain some smaller set of things? And then how do you choose those things? And so that's something lots of people, including my colleagues and I, are working on, but I don't know that anybody has anything very compelling to say yet. So people are trying stuff, and if that's what you're interested in, we can talk about that. Let me switch gears and say that if I can't build an explicit microscopic model for 1,000 neurons, maybe I can exploit the idea from the normalization group that things get simpler if I look on more macroscopic scales. So let me think about doing some sort of RG-inspired data analysis. And you'll remember the basic idea was that if I have things that live on a lattice, what I'm going to do is I'm going to take, for example, plaquettes and replace those by coarse-grained variables. The problem is, and then I'm going to do a bunch of stuff, right? But actually, if you want to follow this path, you already have a problem, because neurons don't live on lattices. And as I mentioned yesterday, locality is not a very useful concept, because neurons are extended objects, and the tree of dendrites covers an area or a volume that contains thousands of other neurons. So what are you going to do? Well, the idea that we had, and we had two ideas. One idea was to say, well, look, suppose that I had spins in a magnet and they really lived on a lattice, but somebody had scrambled the lattice, Or alternatively, you'd given me the configurations of the spins, but they're just labeled 1 to n, and I don't actually know their geometry. What would I do? Well, the answer is that the most correlated pairs are the ones that are next to each other. So suppose we measure the correlation coefficient well, suppose we measure the covariance matrix and then we measure the correlation coefficient, which is CNM divided by the geometric mean of the diagonals. And we say that the way to find out which neurons are next to each other on the sort of hypothetical lattice that underlies all of these dynamics is to find the most correlated pair. And then the next thing I do is I take those two neurons out and I say those are next to each other. And then I go and I find the next most correlated pair and I say those are next to each other. And I do this until I have n over 2 pairs. And then I say, well, what would I do if I were doing it in the normalization group? Well, I'd average them together. So that's the whole strategy, and that's a strategy you can repeat over and over again, just like in the averaging in space, right? So I take sigma I plus sigma j star of I, where j star, to define I, right, where j star of I is the arg max of C with respect to j of Cij. And I do that iteratively. And then I can do it again because I can take sigma tilde I, sigma j star star of I tilde, and that produces sigma I tilde tilde, right? And what I'm doing in this process is I'm grouping the neurons together, first into groups of 2, then into groups of 4, and so on, right? Then into groups of 8, powers of 2. And I've made a kind of cluster of neurons, and I'm keeping track of a variable which is the activity of that cluster. But I've shaped the clusters by trying to have them be neighbors, right? And now I can ask, what happens? So let me just mention parenthetically that there's a completely different way of doing this, and I'm not going to show you any results, but some of you might be amused. How many of you have ever studied the normalization group in a sort of field theoretic context? Good. So you all know, well, 30% of you know, and the rest of you can ask them, that there's another way of doing the normalization group. And to try to be as understandable to the other 70% as possible, suppose I take this configuration in space and I Fourier transform it. So now I have short wavelength things and long wavelength things. And I say, well, the details that I'm averaging over when I do this coarse graining, they're all short wavelength things. So let me take all of the short wavelength components that I need in order to do the Fourier reconstruction and average over those and build back a description which only has wavelengths that are longer than some scale. And then let me move the scale. So in the field theoretic context, this is called momentum shell renormalization group, but actually it's more general than that. And in a system with translation invariance, momentum is special, or wavelength is special, because the Fourier modes diagonalize the covariance matrix. So we could diagonalize the covariance matrix. They have a name, and they're called principal components. And I could average over the principal components that make small contributions to the total variance and ask what's left. So the usual way you do this is to ask how many components should you keep. But what the normalization group invites you to do is to ask what happens as I move my cutoff. Okay? So there's an alternative to this, which is momentum shells or Fourier modes, or what is essentially PCA. I'm assuming that if I ask how many people know what PCA is, I get more than the field theorists, right? Oops. Can we actually do that just so that I know that I haven't just made a terrible mistake? How many of you know what principal components analysis is? Good. So actually not vastly more than the number of people who know about momentum shell normalization group. I really should have, no, it's partially overlapping. I think I really should have calibrated myself a little better at the beginning, so I apologize. But hopefully, I haven't said anything totally incomprehensible yet. Wow, that was really interesting. So what am I going to do? Let's actually step through examples of what happens. So we're going to take the data from more than 1,000 neurons, and we're just going to do this. We're going to do this exercise. And we're going to keep grouping the neurons into clusters. And we're going to ask about the statistical structure that emerges. So let's see what that looks like. Well, one thing I can do is to look at the variance of activity in the cluster of size k. So I've grouped together 16 neurons. And if I look at the variance, and I'm summing their activity, or averaging, let's say we're summing it to keep it simple, and I look at the variance of that over time. And I look at that averaged over all the clusters. So if I do that, and I look at that variance as a function of cluster size, if the neurons were completely independent of each other, the variance would be proportional to the cluster size, right? Because every neuron is doing its independent thing, the variances add. If the neurons were perfectly correlated with each other, the variance would be proportional to the square of the cluster size. What you see across more than 2 decades is a power that's somewhere in between. And it's a pretty good power law, right? I mean, this is a law. It's a log-log plot, so you should be careful, but those are the real error bars, and the straight line really passes through all of them. More subtly, if I look at the probability distribution of my coarse-grained variable when I'm at scale k, one possibility is that it's 0, right? Because it could be that at this moment, all k of the neurons that are in this cluster that I've built by coarse graining are all silent. And when I do this rescaling, I want to be sure that silence still means silence, so I don't shift my baseline or anything like that, right? So there's a probability that they're all silent, and then in that case, if all of the individual neurons are silent, the coarse-grained variable that you build by adding them all up will also be 0. If the neurons were independent of each other, then this probability would fall exponentially with k, right? And what you see is that this probability falls, the log falls as a power of k, but not 1. It's a little bit different, and again, it's a very good power law. If you think about if you go back to here, and you think about this probability distribution, if you've arranged it so that all of these terms are 0 when the neurons are silent, which you can always do because you're in this 0-1 representation, then the probability of silence is 1 over the partition function, which means that the log of that probability is the free energy. So what you're really plotting here is the free energy as a function of the size of the system, and you notice that it's growing more slowly than the size of the system, which would mean that if this kept up, if you got to an infinitely large system, the free energy would per neuron would be exactly 0, which suggests that there's something going on underneath that's enforcing that. But of course, nobody screamed, but this better not be the whole thing, right? There's some probability that it's not 0, and then that distribution has a shape, and it's convenient to normalize so that the average non-zero value is always 1. And then what you see is that as you coarse grain, the distribution shifts, but by the time you've gone through 32, 64, 128 steps, the beginning of the distribution is starting to converge, and it's converging on something that's more or less exponential here. I should say that in this particular figure, what was used was the actual fluorescence intensities from all the cells. So these are continuous variables. They haven't been binarized. You can do it all over again with the binary variables, you get the same answer. So what is this telling you? It's telling you that as you coarse grain, the distribution of local variables is flowing toward a fixed form. So I'll remind you that this was the core of the idea of the normalization group, right? That somewhere out there in parameter space of your models, there's a fixed point, and if you're on the trajectory that leads to that critical point, then you will flow toward it, whereas if you're not, you'll flow away from it. And by the way, you all know an example of this. It's the central limit theorem, right? If you take independent random variables and average them together, whatever just with any finite variance distribution that you started with always flows toward being Gaussian. What's non-trivial in the RG is that you're grouping together variables which are correlated, and the correlations have a kind of self-similar structure to them, so that you end up at a fixed point, but not the Gaussian. And you can see that this is very definitely not Gaussian. There's another one. So there's an A and a B. Well, there's a sort of 2A and 2B. There's a third one, which is about dynamics. So in systems where you're doing your coarse graining in real space and interactions are local, you understand that the time it takes for correlations to decay or for information to propagate depends on the length scale over which you look. So for example, if fundamentally what's going on is that things are diffusing through the system, then if I've averaged over length scale L, I expect that the time it takes for correlations to decay away goes like L squared. So I expect that correlation times go like the size of my cluster to some power. Now what's interesting is that we don't have a notion of locality in space. All we're using is the strength of correlations. And we're building clusters to be maximally correlated with each other. But it still turns out that the larger clusters decorrelate more slowly. So they retain memory for longer times. And as Mauro showed you, an important part of the predictions of this whole way of thinking, which in particular cases, of course, you can make absolutely precise, is that not only do things generally scale with each other, first of all, those scalings are supposed to be exact, which is challenging with real data, even in condensed matter physics, by the way. Often, the scaling, for example, of the way correlations decay in time, the characteristic time scales with the length, but the shape of the correlation function stays the same. And in some ways, that's an even stronger prediction, right? Because why should the correlations in clusters of 128 neurons look like decay with the same function as in a cluster of 64 neurons? But you can see that they do. And so these are the results. So you see that larger clusters decay more slowly, but if you rescale by the correlation time, they have the same form. the correlation time grows as a power of the cluster size. It's a very small power, and one can think about why that's true. It has the unfortunate consequence that it limits the dynamic range of timescales that we have access to. The short times are constrained by the dynamics of the indicator molecule itself. So you're not going to be able to, you wouldn't be able to go much below this. It would have been nice to go further. In some ways, this might be the most important thing, although it's the most tenuous. Because what it says is that by being in whatever state this network is in, if you look across more and more neurons, you get access to dynamics on longer and longer timescales. And you know that one of the problems of understanding how neurons generate behavior is that neurons do things on the millisecond timescale and we do things on the second timescale, right? So the fact that you can get this sort of timescales coming out which are vastly longer than the microscopic timescales, that's not generic, by the way. In general, if you hook n things together, each of which relaxes on timescale tau, the whole thing relaxes on a timescale which is still of order tau. It's only when you tune the system close to something like a critical point that you get a spectrum of timescales that goes out to very far values. So where I want to end is here. Not a very pretty picture, but it has something quite important going on. So let me see if I can remember. So this free energy, right? We said that the free energy goes like k to the power beta. And so we have a number for that. You can also, when you build a cluster of k neurons, you can look at the correlations inside the cluster, which is a good thing to do because the cluster might be of size 100, and a 100 by 100 correlation matrix you can measure. You can't measure the 1,000 by 1,000 one, right? And what you find is that as you go from looking at 32 clusters of size 32 to 64 to 128, until finally you run out of steam, you find that the shape of the eigenvalue spectrum stays the same if you rescale by the number of dimensions. And the beginning of that spectrum is a power law, and so mu is that power law. Z is this dynamic exponent. Z with a prime is what you get if you try to estimate the dynamic exponents using the sort of Fourier PCA methods. And those should be different, and the amount by which they're different. If you Z tilde and Z tilde prime should have a relationship to each other that depends on mu. And that works, but the error bars are big. And finally, alpha is this slope of the variance of the activity. So why am I showing this to you? I'm not showing it to you because I have a theory for any of these exponents. I'm showing it to you because you will notice that the error bars are very small. I draw your attention particularly to this one. The error bars are 1%. You could say that's cheating because your naive expectation was that this is equal to 1. So you didn't measure 0.88, you measured 0.12. The difference from 1. Okay, then your error bars are 10% of the value, which is still pretty good. These are bad. These are a little bigger. But the thing that's really impressive, I think, is that these are 3 different mice. Of course, on different days, completely different experiments. And if you think of the error across experiments, it is essentially the same as the error of your estimate within a single experiment. So you're seeing scaling behaviors that extend over more than 2 decades. The data are accurate enough to determine the exponents to within, well, however you want to describe this, 1 or 10% accuracy. And even more importantly, if you just do the same experiment in a different mouse, you get the same answer within the error bar from a single data set. So that except here, by the way, just to be full disclosure. We have absolutely no idea why that is. This suggests that you really are uncovering a scaling behavior that's meaningful about the system, right? We don't know what it means yet. We don't know exactly how to interpret it. We don't have a theory for the exponents. But it tells you that you've uncovered something about the collective behavior of these networks, which is sort of precisely true across animals. And I will remind you that if you think about, what does all this have to do with criticality? As Mauro emphasized, in one point of view, something's supposed to have a power law distribution. And then you realize, well, maybe not. Actually, I've always found that part of the avalanche story to be problematic, because if I look at a ferromagnet at its critical point, the distribution of the number of spins that are up is not a power law. Other things are power laws, but not that. So, it's not enough just to point to something, as he emphasized, right? It's not enough to point to something and say, oh, look. No. You have to check many things. They have to be consistent with each other in some way. In our modern understanding of critical phenomena, the definition of a critical point is that it's a fixed point under the renormalization group transformation. And so the thing which is not here, which was a couple of slides back, is that the distribution of local activity in neural clusters approaches a fixed, non-trivial, which is, say, not Gaussian form, as you corkscrain. And if that's right, then that means that the model that describes the dynamics of the network is at a fixed point of this renormalization group transformation, which means that in our usual understanding, it's critical. Now, this could end when somebody records from 10,000 neurons, right? We could all be over. That's that. There's lots of things that can go wrong. But I think the thing that inspired us is that in the same way that when we sort of the first try with maximum entry methods produced things that sort of were encouraging and consistent with experiment and led to lots of people doing many different things, which of course I haven't had time to talk about. The sort of first try with these renormalization group inspired analysis methods also gave us things which are sort of what you would have hoped for, the emergence of a fixed distribution and scaling along the way. So let me stop there and thank you.
Thank you. If you do these for flocks of birds, are they critical?
So let me say a few words about criticality in flocks. As some of you will know, there's been a big effort by the group in Rome, led by Andrea Cavagna and Elena Giardina, to look at to track the positions and velocities of all of the birds in a flock as they fly by over the piazza, which is in front of the main train station in Rome, and it's a very charming location. In order to do the experiment, you climb up on the roof of a historic old building. Anyhow, there's a lot of stuff going on in that work. If you look at, and so all the birds is 1,000 birds in a single flock of order. And so if you look at, so every bird is carrying around a vector, which is its velocity. If you don't worry about how fast they're flying, it's a unit vector. And if you measure the correlations between those unit vectors, you see that they're scale free. So they have a funny form as a function of separation, which we could talk about. But the important point is that there's no characteristic scale except for the size of the flock. So if you look at the correlation functions from different size flocks, they fall on top of each other, all that stuff. Okay. As Andrea likes to say, you shouldn't be too excited about that because birds knew Goldstone's theorem before we did. if you write down a probability distribution in which variables are directly dependent only on spatially nearby variables, okay, that's a pretty big class of models, right? It's a field theory with local interactions, right? But you should remember, for the sake of our applied mathematician friends who don't know things about field theory, right, that that's a very big class of models. Then it's a theorem that if you're in 3D, you can break a continuous symmetry, but you'll have long wavelength fluctuations, which are essentially scale-free. So massless excitations. And that's what you're seeing. And we constructed the maximum entropy model that's consistent with the local correlations, and that works perfectly. And that's because of Goldstone. I mean, it needn't have worked perfectly, but the reason you get the long-range correlations right is because of Goldstone's theorem. So that's not a signature of criticality. On the other hand, if you remember that the birds don't have to fly at fixed speed, in fact, they can't, you can ask about the correlations of fluctuations in speed. And those are also scale-free. And there's no symmetry that, that does that for you, right? You're not breaking a symmetry when you decide to fly at a particular speed through air, right? Somebody usually asks, in a physics audience, somebody usually asks a question about Galilean invariance, right? So fixing a speed is breaking a symmetry, but not when you're moving through something, right? It's standing still is as you may have noticed, right? Standing still is different than walking at constant speed, okay? Despite Galileo. So if you try to build models that capture those correlations, those models in some sense have to be near critical. Now there's different ways of doing it. We did one which probably wasn't right. And since then, Andrea and his colleagues have gone on to do other ones that sort of capture more of what's going on. What we didn't do was the RG thing. And part of the reason is that flocks are kind of, the interactions really are kind of local, we think. And the shortest dimension isn't that large. So you don't have as many, if you coarse-grained, pretty quickly you'd think the flock was two-dimensional. And that would be weird, right? Because if you average over a scale like this and the thing's only this thick, but it's this wide, then you're doing something funny. So it's maybe not a good idea, but not such a bad idea that we shouldn't have tried it.
May I complement this question now that you gave this answer? Synaptic connections among neurons are more or less fixed in the time scale of those experiments.
Yes.
As for the flocks, who's connected to who or connected to whom could change, right? So they.
So.
Does that happen?
There's a.
Have they measured that?
They're Bialek. So, in the discussion after Monday, somebody asked me about whether maximum entropy models are restricted to describing systems in equilibrium. And I hope I wasn't too rude when I answered, because the answer is no. But that's a common confusion. You're describing so in the simplest case, you're describing the probability distribution. This eventually gets to your question. Give me a second. In the simplest case, you're describing the probability distribution of states taken on at one moment in time. You have said absolutely nothing about the dynamics for which this distribution is the stationary distribution. In particular, you certainly haven't told me whether the dynamics obey detailed balance. And you can have, well, there are infinitely many dynamical models that lead to the same stationary distribution, right? I mean, one way of thinking about it is that if you're Markovian and you have k different states, I've told you k numbers, but the transition matrix has k squared numbers in it. So, it's a constraint, but it doesn't tell you anything about the dynamics. And in fact, one of the first things we checked when we did this stuff in the retina was that the dynamics of moving from one state to the next does not look like Brownian motion on this potential. which, I mean, maybe that would have been great, because then we would have gotten the dynamics for free, but it's also not very plausible. Okay, why did I use this to answer your question? It's because you know, the whole field of active matter, the sort of at the core of it is the idea that you're breaking detailed balance, and in the context of a flock, right, you're changing your neighbors. And one way to think about that is that if you look at the effective interactions between birds at a single moment in time, that can be long-ranged, because the bird who's next to you now, her direction depends on who she was near sometime in the past, and that could be very far away. And so if you take those effects seriously, you should not be, even though the interactions microscopically are local, the stationary probability distribution should not be described by a local model. And in fact, you know this because one of the first things that was discovered was that in 2 dimensions you can polarize. And everyone always says, well, that means that it's because you're not in equilibrium. Well, it also means that you can't write down a local model for the distribution at one moment in time, because it would suffer from all it would be subject to the theorems that tell you you can't break a continuous symmetry in the equilibrium case. So we built a model in which there are only local interactions, and it worked. Reproduced all the correlations. My friends in Rome had the good idea to say, well, suppose that instead of matching the correlation with your average over a small neighborhood, you matched your correlation with your nearest neighbor, and your second nearest neighbor, and your third nearest neighbor, and you built a slightly more complicated model that did that. The answer is that the coefficient that you need to tie the neighbors together decays exponentially as the distance gets larger. So the best fit model really is local. And then you realize that there's a question of timescales, right? So if birds are constantly changing their neighbors, then the active matter effects are very strong. But if you relax to be more or less parallel to your neighbors before they've had a chance to swap, then you're in a kind of quasi-equilibrium. Strictly speaking, not, but close enough.
So just to get that right, based on what is done, without the RG part, it is near the flocking transition criticality.
Ah, no, that's really interesting. One of the reasons why the flocking problem is so interesting, and I decided not to talk about it because I don't have anything new to say about it. One of the reasons it's so interesting is that okay, if I think that all the birds are flying at the same speed, then I write down a model for the distribution of a collection of unit vectors. That has a critical point, but that's the critical point that separates ordering the flock from not ordering the flock. Of course, it's a second order. In some models, it's a second. In the models we wrote down, it's a second order transition. So ordering is the emergence of order, right? And you know, actually, both by looking and by constructing the model that matches the correlations, that you're deep in the ordered phase. So now you should be even more, so you say, deep in the ordered phase, but I get long-range correlations. That's okay for the Goldstone mode. That's okay for the orientational fluctuations. But this makes it even more difficult to understand the speed fluctuations, because in order to get long-range correlations and speed fluctuations, it feels like I need to be close to a critical point. But what's on the other side of that critical point? It's not disordering the flock, right? It's not the transition to polarizing the flock, because I'm way past that, right? So somehow I need to think about an expanded phase diagram, and so there have been efforts to construct that. But
Thank you.
Yeah, as someone who was embedded in Rome for a while, the Romans think swarms are critical for the ordering transition for
yes,
flocking.
yes.
And they have evidence for this. But flocks, they believe, are like, I mean, at least for the ordering, are like spin waves. You know, you're looking at something very low temperature. Almost zero temperature, in fact, the way they're trying to treat it. There's a recent paper that they compare it to a Fermi pasta Ulam model, in fact, at low temperature.
I think the last time I did one of these schools, Andrea and I both lectured, so that was fun. But anyhow.
Any other question? So if not, let's thank again.
Okay.